This is Mr. Houston coming at you with a little flipped assignment here on equilibrium. Now what you're seeing here is a particulate model that is showing two reactions. One of these, A, is going to be, which are the red ones, and then you'll notice right there that some of the red ones are going back to A. There's somewhat of a constant temperature, and if you look up here, there's more of the A than there is of the B. But over here, the concentrations are pretty close to the same. So even though they're going back and forth, the rates of which A goes to B and B goes to A is constant, which means their concentrations, and if we were to have more of these over a given period of time, would stay pretty close to being the same. This is what we call a dynamic equilibrium. Now, a dynamic equilibrium is a little different than something called a static equilibrium. And a static equilibrium is kind of what we see right here. If you're on a seesaw, okay, so so when you're on a seesaw, one of the things that you notice is that the gravity is pushing down, and the kids are balanced, or I'm sorry, the kids are going down because of the gravity, and then this is keeping it up, and that's called a static equilibrium. The one we saw is called a dynamic equilibrium. Okay, so let's talk about what's going on here. Now, first of all, this is a little tough to see, and I apologize, but what we have here, if we were to look at that reaction that we just had, we would see the reaction rates here. When I first started it, there was a whole bunch of A, none of B, and then over time, the reaction rates got to be the same for A going to B and B going to A. And down here, which you can't see, what we just cut off, is the time factor. And so the equilibrium portion we're looking at is right in here. The next thing that we could look at is this. So here's an actual example. I take equal amounts of water and carbon dioxide. The concentrations start here. We have none of the products. As soon as I dump them in, they start to mix. If we keep track of them somehow, what we see is we drastically reduce over time the concentrations of the CO in the water, and then the CO2 and H2 go up, and then when those concentrations stay constant, we have what we see again in that model that we showed from the beginning, what we call a dynamic equilibrium. This occurs in a lot of different places in chemistry and in nature, and that's why we need to take a look at it. If we were to try and do models, again here, water and carbon monoxide, right? That's all we have at the beginning. Over time, notice we're getting a little bit less of the carbon monoxide and water, a little more of the CO2 and the H2. And then finally, when we get to C and D over time here, concentrations. Now they may jump back and forth a bit, but if we count them all up, the concentrations of reactants equals the concentration of products. And again, it's this dynamic equilibrium that we're trying to describe. Okay, so here's what we're doing. And again, the key part that I'd like you to get down is when the equilibrium is reached, the rates of the forward reaction will equal the rates of the reverse reaction. It doesn't mean that the concentration of the products equals the concentration of the reactants. It just means that they're constant. Now, this is the part where if you're going to do anything, you need to stop what you're doing and make sure to write this down. Not so much number two, we may not get into that, definitely number one. The number one thing that you need to get is when we write this expression. So if the concentration of the products is constant and the concentration of the reactants are constant, then we have to write what's called this equilibrium expression, and the ratio of those gives us a constant, and we have to know the conditions. That's key, and we'll find out why. Okay, so here's an example, and I think this is a pretty good one. Let's say I take a bunch of A and B, dump it in, it goes to C and D, and then over time C and D go back to A and B, and we have a equilibrium at a specific set of conditions. The way that you write the equilibrium expression is you take the concentrations. Now these brackets means moles per liter. The coefficients are the exponents, okay? And it's the products over the reactants. Again, you have to have moles per liter, and it has to be, the coefficients are the, turn out to be the exponents. By the way, number one place people get tripped up with these problems in accelerated, even in AP, is that if we have a solid or liquid, we cannot write that as a concentration in moles per liter. Therefore, we just drop it out of the equilibrium expression. Okay, so this is key. You really won't be able to do the problems unless you're able to write these. Here's an example. It says write the equilibrium expression for the reaction below. Nickel goes plus 4 carbon monoxides is in equilibrium with nickel, what is that? Nickel 4 carbon monoxide, I think, or carbonite, maybe. Anyway, here's the balance equation. Okay, so how is this written? Okay, this is a gas. There's no coefficient, and if it's a gas, we can get moles of gas per liter. That goes on top. Solid, you drop it. You can't get moles per liter for a solid. I could write this in these brackets here. Again, these brackets indicate moles per liter of the CO, and the exponent 4 came from that coefficient. Same way every time. Now, if we were to do this as gases with pressures, we could do the same thing, but with just partial pressures. Here's a good example. Carbon dioxide goes to carbon monoxide and O2. It's a balanced equation. We have to have that every time. Partial pressure of the O2 gas, partial pressure of the carbon monoxide squared over the partial pressure of the carbon dioxide squared. Again, products time over the reactants gives us the equilibrium constant for the pressure. Okay, now, what does this mean? How do we interpret it? Well, I'll tell you what, let's go back to our little experiment here. Okay, so let's take a look at the concentration of the products over the concentration of the reactants. Right now, if I can somehow get out of this, let's see, there we go, and go back to my little experiment, which unfortunately I don't have, so forget that. But typically what it means is, when we're looking at this, is if I can see this, if K is greater than 1, that means we have a lot more products than reactants. That means the equilibrium is shifted to the side of the products. If K is really small, that means the reactant concentration must be huge and we have very little products. That's going to come out in a lot of places. Now, when we go into acid and base chemistry, there'll be equilibrium expressions. It's called Ka, and A just means it's an acid or base. When we dissolve things, okay, the way the equilibrium and how things dissolve and go into solution, that's called KSP. It's all basically the same thing. It's just describing the reaction a bit more. Now, when we solve these problems, we'll do ice tables. So as an example, here's a classic case. Here we have this in gases. It's a balanced equation. We could write the equilibrium expression. It says you start with 2 moles of hydrogen and iodine, you mix it in a plain vessel, you get 3.5 moles of HI are produced. We can assume that that's at equilibrium, that this 2 moles is a start. What's the value of Kc? Now, this is the key. It's important to realize that not all of the reactants are converted to products in reversible reactions. Some reactants will remain at equilibrium. What does that mean? Well, we have this thing here called an ice table. And by an ice table, let's think about this. This right here, this where it says start right here, this would be initial. So we'd call it I. C stands for what is the change that occurs. And then F, or what it would be at equilibrium, you get ICE. That's where you get this idea of an ice table. And so here's what they're trying to show. They said in this problem, hey, you start with 2 moles. At the very beginning, you don't have any product. Things react, you wind up with 3.5 moles of my product. I must have had a change from 0 to plus 3.5. If I add these two together, I get 3.5. How the heck do I add in the other parts? Let's take a look. Okay, so if we use the molar ratio to get that 3.5 moles of HI, because it's a 1 to 2 ratio of moles of HI and for every 2 moles of HI, I only use up 1 mole of H2. I had to use 1.75 moles of H2. So here's how I filled this out. I said, okay, look, they told me I have 2 here, and 0. They gave me the information that at the end I have 3.5. Excuse me, I'm going to have to hit pause for a second because I have a phone. Okay, I apologize for the phone call. So, okay, so if we gain 3.5 because of stoichiometry, because it's, you know, for every 2 that I gain here, I must have used up 1.75 here of my, because it's a 1 to a 2 ratio, right? So if I use 1.75 here, that will always give me 3.5 moles here. And so then I wrote that down. I said, hey, I must have lost 1.75 here. I lose 1.75 here. That's the change. Now we just add everything up on the bottom. And when I add everything up on the bottom, 3.5, 0.25, 0.25 moles per liter. Hey, good news. We now have the concentrations at equilibrium, which means if I have the concentrations at equilibrium, I have 3.5 here, 1.75, 1.75. I can find the equilibrium constant. And because I'm guessing, and I didn't do the math yet, but I'm guessing it'll be bigger than 1, it favors the products. Okay, that's what that means. Now, the last thing we need to talk about is Le Chatelier's principle. And this had huge implications. And the biggest thing here, and we'll do some demonstrations in class, if you have an equilibrium, you have to say what the conditions are, but if you put a stress on it, it will react and change to minimize the stress. Okay, so here are factors that can affect it: concentration, temperature, pressure, and adding a catalyst. Now we're going to talk about these first 3, and essentially, however, it always wants to get back to equilibrium. So as an example, let's take a look at this one right here. Okay, so we have this reaction, carbon monoxide plus 2H2 makes methanol. It's an exothermic reaction. Otherwise, you can think of this heat as a product. Okay, so what happens if some of the methanol vapor is condensed and removed from the reaction vessel? Okay, so it basically says this. Here's the concentration of methanol. I take some away. I have less than what it would be at equilibrium. The reaction says that's putting a stress on it. I want to get back to what it was at equilibrium. So it's going to shift and start to make more methanol, and it's going to force the equilibrium to the right. Okay, so it'll readjust to go to the right. Here's one. The pressure is increased by decreasing the volume of the vessel. Now, if we think about this, the products only have 1 mole of gas. The reactants have 3 moles of gas. 3 moles takes up a lot more space than 1 mole. So if I add pressure to it, it's going to say, look, I really don't like having so much pressure, or once I have that pressure, it would be better for me to have less gas because I can fit it better in a small space. So it'll shift, adding pressure, shift the equilibrium to fewer moles of gas, just like decreasing pressure will shift it to more moles of gas. And finally, the temperatures increase. How does that going to change it? Well, if the temperature is a product, you can think of this as like a chemical almost. If we put more of it on this side, it's going to say, wait a minute, I've got too much. I need to get rid of some. So to do that, it's going to want to shift and use up more of the product and shift the equilibrium over to the side of the reactants. Okay, so we'll do this in class, and you'll see how this works. Make sure to take notes. I would also say, if this is a little confusing, we'll certainly go over some stuff in class. Bozeman Science on YouTube. He's got a great channel. He also does equilibrium. Haven't seen the one from Khan Academy, but I hear that's pretty good. Thank you and have a nice night. Don't forget to get notes over this and bring them to class.